everyone. Today we will start to design single photo frame 3D compare with 2D from previous tutorial. You watch my previous tutorial about how design single photo frame by using Freenet photo frame 0.3 and compare with the ConSteal 2D. And today we will compare about 2D frame and 3D frame and what is different when we design in the 2D frame like this one and compare with the 3D frame. Now today we will start from 3D model, and you see here this is a complete 3D model. We design everything at the same with the Freenet software. Okay, we have also the pressing L section and column is IPE 550. I show the section to you. Okay, column is 550 and for the beam is IPE 500. Okay, we keep everything is the same with Freenet software, and we will try to compare each other between the Freenet software 3D photo frame by using ConSteal and 2D photo frame by using ConSteal, and how my percentage is different. Now I have to turn on the cross section. Okay, you see here the span is 34 meter length and the column height is 6 meter length, and for the overall height is 8.2 meter length, and one spacing is 6 meter. Okay, and the total length in the direction is 42 meter, and we will start again from 2D frame because in the previous tutorial I provide you the correct, the incorrect height of the page. Now I correct it again to the height with the same as in the Freenet software. Okay, is 8.2 high. Okay, and the cross section we keep it the same, but in the model it designed other 3D model, but in the previous one we compare it with the 2D model in ConSteal. Now we continue again with the 2D, and we will try to correct from 2D and start continue with the 3D, and we have to input the support. Okay, the very important is the location 1, 2 and this location 1, 2, 3. Okay, in this 3 location it is very important to keep our structure stable and out of plan. Okay, and in here we just like to model the purlin, upper purlin, and to add the lower restraint to the torsional lateral buckling. Okay, so we have to add at the bottom. Okay, at the bottom, and we skip one and we add to the bottom again, add to bottom again, and for the column we applied it in the same concept. We has other Z section, and this one we add a restraint. Okay, now we try to do it the same with our concept in design in the Freenet software. Okay, and now let's start again from compare here to analysis, and I want to run analysis again. Okay, now you can check about my analysis. Okay, have to check analysis, and you see the alert message appear here is there is no relevant buckling result. You see here when you run it into the analysis, the mistake appear, and after we complete the we run compare with the 3D, and you can compare the mistake again. Okay, no relevant buckling result. Okay, now we have to check about the analysis. The buckling result also. Okay, this one also so for the plastic hin and first order analysis. Okay, you see here the plastic hin. This plastic hin developed in this section is very important in location 1A in the column. You see here in the column. Here the raster, and this from here is the hole. You see here is hole, and the location is the joint between the hole and column. So and the location appear the plastic hin. Now you can check plastic hin in the location. It is very important to be sure your construction can be resist the moment, the apply load, the electrostatic buckling, and this thing you have to make sure it is the serious location. You have to take care about it. And this one also the critical one. Okay, for the plastic hin developed in here. So you at least have two pressing out of line. Okay, at least you have to press in this one and this one at least. So you have at least two support and one out of line pressing here, 1 2 3, by using the tube section or by using the rectangular section to press from one plane to another plane and the location. Okay, now we have to check about the diagonal to make sure everything is fine without the error. Okay, it's good. Now you can check again about the analysis, everything here. Okay, the combination, but I showed you already in the previous tutorial. Now I just take a quick about to compare it again. You see here, this is the result after you complete correct the model from previous one. Okay, you can check here everything here. Now we have to go forward to the 3D model, and I will explain you why we have to add pressing and why we have to add the other lower and upper pressing. Like this one, we have to add the pressing from the raster, from the raster to the purlin. Okay, why we have to add the pressing? Okay, why we have to add the pressing, and why we have to add the pressing? Okay, and why we have to add the pressing? So we will find the answer together. Now we have to start from the first one. This one we have only pressing in bay to bay. Okay, in bay to bay, and we also had other section. You can check here other section. Okay, that we checked previously about the plastic hin. Okay, to make sure our structure is stable in out of line. We have at least 3 locations, this one and this one. Okay, this one. Okay, this one and this one. Okay, now I have to show you about the tie. Okay, I call it the tie. Okay, you has at least 3. Okay, 3 location at least, and 2 support. Okay, at least 2 support, and to make sure the support can be receive load from the y and z direction, and prevent torsion about its own axis or column. It is very important. And you see here we there the purlin, the column, the raster, the hole, and the pressing, everything we try to compare with the previous software. Okay, finish over. Now you see here in our there we do not have the restraint at the bottom of the raster and connect to the purlin. In this case we will try the whole model is the same. Okay, in the whole model now we have to compare it. Let's start with the analysis. Okay, now I have to run analysis. Maybe you have to wait a while for analysis before it complete. It is very important for us. Yes, it is very important for us. Now you see here it is the first order analysis, and we can show about the moment, about the internal force. Okay, you can show everything from here. Okay, now I just take a quick. Okay, the result is similar with the Renesovia. You can check the previous tutorial about how to design in the Renesovia. You can see here 637 kilonewton meter, and in this one now we have to focus about the buckling. Okay, I want to show you about the buckling. You see here about the buckling. You see here this is not pressing. You see here I don't have pressing because the previous one I there it with the pressing, and I delete it. Now I just run it without the pressing at the bottom here. So now you just to keep in mind that if there is no other pressing at the bottom plane or the raster, and for the column are the same. Now you have to continue about analysis, and you have to check. You can check your raster. Your raster is deformed out of plane with twisting. Okay, with twisting your section is rotate. Okay, you see here I can call it the effect is lateral torsional buckling appear in the raster, especially at the joint between the column and the raster. You can see here the location is very serious. Okay, very important to analyze and to make sure your section is not rotate at the bottom. So you have to add the pressing. Okay, I call it the pressing from the bottom to the top of the purlin. It is very important. Okay, very important. So you see the phenomenon that occur from the apply load. You see here you can see out of plane. Okay, out of plane deformation here. It is very important to make sure the structure is safe. And now we have to try. Okay, you see here the critical load is 0.89. It's very serious. Okay, it's not good below than 1. So you have to make sure your structure is it got higher critical load. Okay, at least 1. Okay, in the case we cannot accept. Okay, we will continue from the combination 1, and H value is from here. Now we to check from other is delocation. Okay, the first one is delocation, and the second is delocation. And now we try to other. Okay, you can check it is delocation, and we check it again. Okay, almost appear at the raster. Okay, now we continue. Okay, the raster and the purlin. Okay, you can check the raster and the purlin. You see here your column is also affect from the raster. Okay, you can check. Now continue. Okay, in the mode okay, seven mode. You can see here the effect up here at the column, okay, at the column. Now you have to check it, okay. You see your deformation also affect from the lateral and torsion. You can see here your section is tweaked from the on axis, okay. It is very important. You have to check about the mode shape, and you know about the shape that structure effect, okay. You can check it the local effect or global effect, but in this one I can't talk it's about the local effect of the member, okay, because okay your section is the column is deformed in column 1, column 2, not whole frame, okay, not whole frame. You can see it is column is deformed, it column is deformed, but it's not deformed laterally, but it's not deformed laterally, it deformed lateral and with twisting the section. I can make sure this section is received by lateral torsional buckling, okay. It is the very serious phenomena in steel structure. You have to prevent this phenomena occur in your structure to make sure your section is have full stability and strength to resist this phenomena, okay. You can see here this one also, okay. So you know the pressing is very important when you add the pressing here to make sure you have the stability in out of plane, and include with the this one and this one is very important, okay, to keep out of plane or the whole frame, okay, stable. Another one is about the pressing from the bottom raster to the purlin. It is to keep your local, again, local section, your local raster to stable from the apply load, okay, not twisting, not occur lateral torsional buckling and this section. So the section will got higher resistance to receive the load. When this phenomena occur, your section will be reduced much load, okay, cannot reduce the apply load anymore, okay. You have to make sure your section is safe, so you have to prevent this phenomena not occur in your frame, okay, in your frame, okay. You see here. Now let's start to the other new one with the same, everything is the same but different from here. If we apply the pressing, other pressing here, and we can call it restraint, okay. That in other software like Start Robot or Sharp Attack, you assign a restraint without drawing it actually, but in Consteel you can do it actually by assign the joint, okay. Here joint to top, joint to bottom, and joint to the bottom or the hinge or the section, and you can add other joint from here, and you can connect each other by the element, so you will got the restraint at here. But in other software you input direct restraint, but it is difficult to check about your restraint and your purlin. You can receive is or not. It is very important when you model it in the whole model. You can check it as the previous one model that I discussed with you. It is very important to check the mode shape, to check the load case to control, okay. You have to check everything here. Now we have the side purlin here, okay. We have the restraint, okay, restraint, and we have the restraint, okay, restraint. I'm not apply for the whole frame because I know it's occur in this location, so I I create the restraint in the location. Okay, so in this location you can skip it. Okay, and our dimension of frame is the same with the 2D frame and with the same with the RUNET software. Everything is the same, and we just to try to compare and to explain you about how important about the restraint here to prevent section, to prevent our out of plane, okay, deformation. You see here I put it the same from one frame to other frame. Okay, and the gap ball in the case we do not add a column or add other beam, so I want to keep everything in like this one. Okay, you can check the model. And for the load we apply it the same with the previous tutorial 2D. Okay, for the dead load 1.8, for the light load 2.4, and for the wind load we apply it the same. Okay, apply the same. Okay, you can check my previous tutorial with the single bottom frame designed by RUNET software and compare with the 2D that we apply with the same load. Okay, you can check the load, light load, and wind load. Okay, so this one will also keep it the same. Okay, but it's different from the 2D. We create the whole 3D model. Okay, whole 3D model, and we ignore about the cable frame. We do not add the element. Okay, you can check here about the dimension of the frame is the same, and the magnitude of load is the same, and the load is the same. Okay, and the combination also is the same. Okay, the combination. Okay, now you have to check about analysis again, and it is very important when you take analysis. You have to make sure after you complete analysis, and you have to check the mistake to make sure no error, no other error. It has error, you have to fix it before you continue to analysis and design. Okay, now you can check about the deformation. You see here deformation, the maximum deformation. Okay, maximum deformation. And now I start from the first order analysis, and you can check about deformation, and you also can check about the moment. Okay, moment, the moment is almost the same, and you can check for the envelope case. Okay, the envelope for the ultimate load combination, you can check here. Okay, here and here, and you can add for the mark. Okay, also this mark and also this mark. Okay, you can add here. Now we have jumped to buckling again. Okay, now let's start with the buckling. I want to check about the buckling. It is the very important. Okay, now we check from the load combination 1 and start from exchange value 1 the same. You can see here the exchange value is 3.83, but from the previous one, when you do not apply the bottom restraint at the column and the raster, you can check the exchange value is 0.89. It is very different. It's around 3.5 times about this there. Okay, it is very important. So you have to check. Now I have to check about the buckling shape. Okay, the exchange value is 3.83. You see here it's occur at the column. The previous one is occur about the raster. Okay, raster when you do not have the restraint. So in the case we include the restraint. Okay, you see here about the restraint. Okay, our restraint and our purlin work together. You can check. Okay, work together, and to reduce out of plane deformation. Okay, you can see here the raster now do not much deformation in out of plane. Okay, you also have, but it's very little. Okay, very little, about 2.7 millimeter or about 1.3 millimeter. Okay, you can check here in the column, but it is for the load combination one. Okay, for the ultimate load, not for V. We just check for the shape. Okay, you can see here shape. Now we have to let's try to add the agent value. Okay, agent value 1 is column in the location, and for agent value 2 is the column in the location. Now we let's try to add the add the purlin. Okay, add the purlin, okay, you see here, do not have other big effect on the raster anymore, because you add the restraint here. They connect with the bottom of the raster to the top of the purlin. You can see it is very important when you add the lateral torsional restraint at the bottom to prevent out of plane deformation, to prevent out of plane that can make your structure, your frame unstable here. So it is very important. Okay, now you know about the pressing, so important. Now you can continue to the combination, but if you design it already, you can check the load combination, the control here. You can check for the 3D, there in this one, the load combination is global stability resistance. Okay, the global stability resistance. Okay, the whole frame. Okay, and when you check from the 2D, it is the plastic interaction resistance. It focus on the section, not on the global effect. It is very important from you analyze it 2D frame compared with the 3D frame. For the larger span like warehouse, long span, so it is very important. You have to check here the global effect. It is very important. Okay, determine your frame, your strength, your stability. So you have to check when you model it at 2D. You see here the utilization ratio is only 83.8. okay, but when you design it at the 3D, okay, as the 3D model is 107.5. okay, and determination, okay, is the global stability resistance, and this one is the local. Okay, the local is the section, the plastic interaction resistance. Now I can click on here and calculate the section. You can see here it is the conservative interaction resistance. Okay, you can check the utilization ratio is 81.9. Yeah, I check about pure resistance, about the bending. Okay, this bending, and for the compression is really little, is 4, and for the minor plastic interaction, you can see here about the measure. Okay, about the bending. Okay, you can check here, and in the case you have to take the percent from the conservative interaction resistance. Okay, if you check about the elastic, you can see it 93.0. okay, 93.0, the utilization ratio for the elastic resistance, but in this section it not designed in elastic resistance. Okay, this design in the plastic resistant. Okay, the utilization ratio is decreased from the 93.0 to 81.9%. Okay, now we had to compare with the 3D. Okay, now you can click on here and it show it the location that the utilization 107.5. okay, is the location. Okay, it below the hinge. Okay, you can check here about the ratio. Okay, its ratio in the column is around 100%, and at the raster you can see here is about 40, 50, and about 40. Okay, and for the previous one, when you do not have the restraint, so you can check about the global check, and we run design in this section, and then we compare with you what is different when you do not input the pressing or input the restraint. It affect on analysis and also your design result. It is very important. Okay, now check here the utilization ratio in the raster is over 100%, and also 100%, and for the column also 150%. okay, 170%. you can check here again location here. So when we do not include the restraint, okay, you can check about the maximum ratio. But when you include the restraint, you can see here the percent is only 40%, 33%, and 42%. okay, it's really good when you just add a little restraint, and you can see a lot of your frame. Okay, your section, your frame. Okay, now I had to click on it again because the global stability resistance, you can see here, it is very important when you know about the load control of your design. Load control of your design. Okay, the load combination one, examination is global stability. Okay, now let calculate section again, and we will check from the elastic current section. General elastic resistance, check here, is 106.5. okay, general elastic resistance. And for the conservative, I now check for the conservative is only 93.9. okay, you remember from the previous one, the value is take from conservative interaction is around 93.9. okay, but in this one the value is not take from the conservative interaction anymore. You can check it again. The value is take from the conservative interaction again is 81.3, 81.9%. okay, but for this section it do not take from the conservative interaction resistance, but it add the one row is the global stability resistance. okay, you can check here the global stability resistance, the ratio is over 100%, and you can check here the alpha for the in plane is 0.97, and for out of plane is 3.83. okay, you can see here it is the resistance about YLC, okay, is 654.94 kilonewton meter. Okay, the cross resistance about the moment, okay, of the moment is this one, and you can check with the René software again. About the column, and you will see the value about the resistance, and we have to compare it again. It is for the raster, and we go down for the column. Okay, it is the column verification report from the René software. This section and the steel strength. Okay, now we have to scroll down. Okay, in this one, the ultimate limit step verification for bending moment about the strong LC whereby is 0.95. okay, 0.95. the resistance of resistance is 654.94, and you can check here is 654.94 is the same. The moment resistance or resistance is the same. But the oscillation ratio is not the same because it includes the global stability. It is the dominant case. It is the very important to control the design, so you can make sure about when you run in 2D frame, when you run in the René software, and what is the difference when you but there is the same, everything is the same, but the difference you can see here when the software has a full ability to check about the global effect. See here, it is very important, so I had to close it. You see, it is we just to compare and check with the other software. Now we have to come back. Okay, come back global. Okay, you can check everything here. This is the dominant. You can check for general elastic cross-section. Okay, the percent so here pure resistance, you can check here. The pure resistance is only 89.6. pure resistance without include other phenomena in this section. And plastic interaction, okay, you can check here. It only 89, and conservative 93, but for the global stability resistance is over 100%, and you can see here the location. Okay, the location here. Okay, location here. Now I come back to buckling, and I come back to buckling sensitivity. Now you can check here about the buckling sensitivity. Our whole frame is you can check here buckling sensitivity. Now I want to check on the column. Okay, you can check here. This one is 91.2%. okay, and this one is no, it's good. If you no sensitivity or the buckling in this column, and you can check for the raster. Okay, okay, you can check here 100%, 100%. Okay, it is very important. You have to add pressing for the raster. Okay, for the raster, and you have to check about the agent value. Okay, agent value, and you have to check about the buckling shape, buckling shape, to know about the locate, to control about your analysis design, to know about the phenomena, to control about your analysis design. In this case, you have add a pressing to reduce buckling. Okay, and for because you have to check about the deformation, about the, okay, you can check here. If you check in the model, it is easy to see about what is wrong. Okay, you can check here about buckling. Okay, so when you see, and you can fit it in the right location. It is very important for film software like Consteer. It has ability to check, so it's very good when you have to apply the resistance. You can apply it the right location. Okay, not it's not extend to full location, because you have know about exactly about location about all your frame. Okay, and you can check for the low combination. Okay, okay, you can see here it's around here. Okay, it's around here, and you can check at the HMSU. Okay, so you can know how to prevent your structure from collapse. Okay, it is very good concept for engineer. Okay, you have to check about your system work, about your member work. Okay, you can check here. Thank you for your watching. Thank you.